Okay, so we were talking about 8 plus 8 here, figured that out.
Yep.
And then you wanted to expand upon this.
Mm-hmm.
So what do you want to expand upon?
Yeah, so, well, I don't remember what I was going to expand upon there, but we originally only got into that because you were explaining something about 256.
Oh, yeah. So we talked about this before with the matrices, and that it was the only way to actually stack these on top of each other is to make sure that the pixels size for this, the matrix, the dimension, I should say, the dimension of the vector, is what's it called? Vector?
Vector, yeah.
So the dimension of the vector.
Technically, if you want to be like super technical, it's a row vector.
Okay, so the dimension of the row vector needs to be the exact same for it to actually start stacking. Because if it's not the same, it can't stack.
Yeah. Yeah, so that's one thing to keep in mind is that if your images are all different sizes, it gets really fucking annoying to store it because you can't just store it into one big matrix. It gets weird. You have to,
you have to do some compression
shit
on
weird shit
with math.
Yeah. Or you have to store them all separately, which gets annoying because then you have to it takes up more memory or there's overhead. So a lot of the time when you're working with data, especially when you're working with images, you want to, make it so that they're all the exact same size because, so any big machine learning data set with images, all the images will almost universally be the exact same size. Like they'll all be 256 by 256 or 512 by 512. Or
I see.
Right, they'll have a very particular size that they all are. And the reason for that is this. It's because under the hood, they're all stored as a big tensor, is what a 3D matrix is called. And then it's just nice for memory to be able to store it like that. So.
Yep.
Okay.
So we then.
So what else did we talk about last time?
So we talked about that.
Let's go into the talking machines thing. So how did that work? In terms of how we store that data?
Shit. I don't really remember because I remember you were talking about the way that this data was
This
stored
one's a little
specifically.
weirder. Yeah.
Is that
This one's a little weirder.
It's based off of weights. So depending on what word relates to what other word, there's a weight between the two. And so it's okay, well, it's kind of like that paper that you guys were talking about where it was talking machines. So say talk, does it really, so say we have a list of words, right? We have, I'm gonna just move it over here,
Yeah.
I guess.
I would say, I think you're on the wrong track. Don't think about weights of words or whatever. Think about points in space. Because I think last time I described the way that this would be represented sort of using geometry as the fundamental way that we think about it. Because, and the reason that I want you to think about it like that is that that'll lead us pretty well into our next discussion.
Okay, so let's then address it like geometry.
So let's actually change the sentence too. So let's say the sentence is the dog
Pooped. The dog was
pooped.
The dog next was pooped into existence.
The cat.
That bitch.
It's kind of a long sentence now, but let's say that that's our sentence.
Yeah.
So let's get into, we know how we want to store data. It's like that, right?
Yep.
Both the images and the XYZ thingy, those are all stored the exact same way, where the rows are all of your individual separate data points and the columns are information about those data points.
Yes.
So if we can, we would like to store the sentence in the same way somehow. Now, initially, it's pretty unclear how we could do that because sentences are fundamentally, it's the fuck. Yep. First of all, what are the data points? Second of all, how do we do that with those?
Right.
Last time, I gave you I didn't explain how we did it, but I explained a little bit of the geometry underlying why it would make sense to do it the way that we talked about. So try to remember what we talked about last time. So first of all, give you a little hint. We're going to say that each word is its own data point. because we have
Okay.
to choose somehow,
Yeah.
right? So we're just going to call each word a different data point.
Mm-hmm.
In practice, like in the real world, there's something called tokenization, which is very particular to natural language processing, but
Yeah.
I'll just get into it a little bit now. So in the real world, the individual observations, the individual data points wouldn't necessarily be individual words, but it would be, you would tokenize the words, meaning maybe the would be an entire token, dog would be a whole token, but
Yep.
then poo and then pud would be two tokens,
Okay.
right? These are all kind of short words, so these would all, each of these
Single
would probably
tokens.
be single tokens, but like thinking is a great example of tokenization, where
You have to
ing
think,
is
and
kind
then
of its
mean by
own
something.
modifier to a word, and so ing would become a token, right? So ing and think. So this would become two data points because ing is sort of useful by itself, right? Like, so it's useful to think of the ing as a separate object that's just attached to think rather than them both being the same object.
I have a question.
Yeah.
So let's say you have the word thoughtfulness,
Mm-hmm.
right, which is like kind of long.
Yeah.
Would that just turn into thoughtful and then ness?
Yeah. That's probably.
Or would
It really depends on your tokenization scheme. There's a lot of different ways to tokenize. Like, in fact,
You also need to remember, in thought, you have thou.
oh yeah. So actually, it might even be like this. Like it might even, right? But like in practice,
I mean, there's so many ways you can do it. You have thou,
Yeah.
you have tough,
Yeah.
you have thought.
yeah. So in practice, it's not like there's a bunch of natural language processing researchers coming in and like thinking about the ways to tokenize each word, right? What happens in practice is that you have these giant models and they're just trained to learn what the best tokens would be. So in practice, these tokens are just discovered by the model itself.
So you use a model to figure out tokens.
Exactly.
To
And then you
use-
use those later to train a model.
Yeah.
But in practice, there's so these days there's these sort of giant tokenization tables that have been discovered by models, and a lot of natural language processing models just use those tokenization
So
tables.
what is the
in
output
beginning.
exactly from these models? Is it just like a number or?
So that's what we're trying to figure out right now.
Okay.
So that's what Daniel and I talked about last time. So
Yeah.
that's what I want Daniel to think about, because we did talk about this last time.
I'll be honest with you, this is the one part I don't remember.
Yeah.
So,
But for our purposes, tokens are the same as words.
yeah.
I just wanted to create the distinction
Yeah,
so
yeah.
that you know that in practice it works like this, but let's just call each of those words a token, and that's
Yeah.
fine.
I'm just gonna get rid of those, and we'll dictate that.
Mm-hmm.
So we need to do geometry based off of this, and we want to transition them.
I don't know if we
into-
need to do geometry, but
But the way to
we're
think
gonna
about
think about geometry while we're making the table, because that's how we're gonna think about making that table.
Did we do like Pythagorean? Did we do?
Yeah, we talked about the Pythagorean theorem last time. Yeah, we definitely did. Do you remember what exactly we
Oh.
talked about?
I don't remember exactly what, but I do remember that we did.
We did talk about the Pythagorean theorem. Yeah.
What
I
did
was
you
like-
talk about?
So,
What was it linked to?
fucking.
I don't want to say it because
Was it?
Daniel's still trying to think here, but I will. I will talk about.
I
that.
think we talked about it like a square plus b square.
Draw an XY coordinate axis.
Okay.
All right.
So we'll just do.
X1, Y, X2.
Uh,
Don't write it like that. And
No.
and why did I tell you not to write it like that? This goes into another thing we talked about last
This
time?
is because the graph is different. It's a different.
Explain
way
it to explain it.
So there's different. There's pretty much different graphs.
Draw two
Um,
coordinate axes to explain.
So say we have a graph that is doing y1. I think we did y2, x1, x2, or something like that. The reason why, okay, y1, x1, and then you have another graph that is just your x and y axes. these two graphs are fundamentally different. You just want to do, okay.
Draw a new thing up there.
Did I have a y up there before or an x?
No. Why? What's the 1? Why are you saying x1? What's the 1 referring to?
The x1 is referring to, was it the dimension? What was the,
Yeah, the 1 refers to which axis you're
yeah,
on. So why did I erase the thing that was up there?
the y1?
Mm-hmm.
Because it's the second axis.
Yeah. And then I also erased the y because why are we calling it y? Because last time we just said it was the x1 and x2.
Yeah.
And we said that x1 meaning the first axis and x2
Meaning the second axis.
Yeah.
Right.
Okay, I can see where you're going with this.
And we'll just do y and x.
Mm-hmm.
And so these are fundamentally two different axes. One is plotting. Okay. One is plotting a point in space. So it's like just
No.
No. Let me just do c². It's killing me. So say I have 2 points in
Yeah.
space. So within here, I have 2 points in space, and what we're doing is we're plotting the 2 points within space, and then I can't remember if we wanted to compare the 2 points. I think we did. I think we wanted to compare the difference between the two within space. And then the other one is not plotting one in space, it's just graphing something. So this is actually like putting an actual point in a physical space.
Yeah.
In a physical 3-dimensional space, where
Yeah.
this one is just graphing something.
Yeah.
So
Mhm.
that's the difference between the two graphs.
Yeah.
Yeah.
So I really want to emphasize that a lot. So because this, and I'm also not even going to call it y. I'm going to call this axis f of x, just to illustrate even further what I'm talking about.
Oh, you're gonna use it as a function?
Well, I mean that's what it is, right?
Yeah.
I think y is. I don't really like y very much because I think it's not really descriptive. Like,
I
what
see.
the fuck is y, right? Like,
Yeah.
is it a function? Is it an axis?
Yeah,
Like, what is y?
So you have
So
a set of axes, and then you're using a function to modify. I see.
So down here, this is about relationships.
Yeah.
Right? Down here, what we're thinking about is this is a way to visualize a relationship between two patterns, right?
I see.
If you move, say I move forward like this, right? And
Mhm.
say I'm walking towards a fire,
Yeah.
okay? Say I'm in a hallway and I'm walking towards a fire, so I can't move in any other direction but forward and backwards, right?
Okay.
And I walk towards this fire and I walk evenly, right? I don't change my speed at all. I just walk towards this fire, staring into the fire's eyes, lovingly.
Yep.
And as I walk towards this fire, I start feeling an increasing amount of heat on my body, right? And in my groins.
I mean, it's to be expected.
Yeah.
This fire is pretty hot.
And so what I can, and if I walk backwards, there's less heat that's on my body.
Until I start
And-
coming.
Until this fire starts coming at me. And so what I would like to do is I would like to say, well, there's a relationship between how close I've walked towards the fire and how hot my body feels.
Right.
Right? There's a relationship between, and like let's just call it x, how far I've moved forward,
Mhm.
right? There's a relationship between x and the heat of the fire, which we'll call f of x, right?
Right.
So, no matter which x I'm at, I'll feel right. I'll feel different.
Yeah.
And so down here, it's about being able to visualize that pattern. It's about a way to visualize the relationship between two things, right? If one thing is dependent on another thing, it's a way to see that with your eyes.
Yeah.
So actually, I want you to graph what I just talked about, the walking down a corridor with a fire.
So as I get closer to the fire, so
Mhm.
we'll call this heat, we'll call it hot.
Yeah.
Hot up top.
Yeah.
And
And
we'll call this-
let's just say the fire is here. That's
Yeah.
my shitty fire. Say
So
the fire's right there.
as I get closer to the fire, I'm interested if we want to do it like in an exponential kind of way, where it like exponentially gets significantly hotter as you get closer.
Mm-hmm.
I mean, that's the way I generally feel when I get close to a fire, touch something, and I go, fuck! So we'll just do it this way.
Yeah.
So as you get close to the fire, you're exponentially going to feel the heat more and more and more.
Good.
So I'll just define this as heat, not hot.
Yeah.
If I can write. This is the curse of being a lefty.
Mm-hmm.
But for all the lefties out there, you keep being a lefty because you're great.
Yeah.
Don't let all these fucking righties tell you otherwise.
So here's so that's perfect. That's really good.
And lefties are perfect.
So here's one thing that I want to. We're going to go off on a little bit of a side tangent because I think this is a great opportunity to talk about what it means, the feeling of an exponential function, in the same way that we talked about the feeling of a logarithmic function.
Mm-hmm.
So fundamentally, and to really understand this, we'll need a little bit of calculus, which we'll talk about later. But without using calculus, fundamentally, an exponential function is something that feeds on itself. Meaning, an exponential function is something where the more of something you have, that feeds into its growth. So it's something where if you have more of it, the fact that you have more of it causes it to grow faster.
I see.
And so when you think about like the pattern that an exponential function is, that's what the pattern of an exponential function is. Think about like, I mean, the obvious one, like sort of a standard textbook example would be like population size, right?
Yeah.
The reason that that's exponential is because the bigger your population is, the fact that the population is big is what causes it to grow faster, right?
Right.
And there's a lot of things in nature that have that property where the bigger they are, like there's something about their size, their massiveness, that causes them to grow proportionally to that size. And that's what an exponential function is. And so when you think about like, is something an exponential function, the first question you should ask yourself if you're thinking about like, something in physics
Is
or
the
like
growth rate?
is not the growth rate, but you should ask yourself an even more fundamental question, which is, does the fact that this thing is bigger, is that the fundamental thing causing it to grow faster?
I see.
Like, is the size of that thing in some way causing the growth?
Right.
And
It's like a virus.
yeah, like a virus. That's another exponential growth thing. And so I think people like to throw around the word exponential growth a lot because, like, they know what that means and they don't know what linear growth is, but they.
Yeah.
If you say quadratic growth, that sounds fancy because they're like, what's quadratic growth again, right? So exponential growth has a very specific meaning, which is
linear growth,
which is
just
that
like-
pattern. Yeah, that's linear growth. So with that in mind, let's think about whether that's exponential or not.
Yeah.
Why?
As you get closer to the fire, the heat is exponentially going up. So as I get closer and closer to the fire, the relationship of me being closer to that fire is making it hotter. And not only hotter, significantly so.
So, no. I don't know how to explain that though. Maybe the fire is not a great example, but being.
As you're getting closer, what you're doing is essentially lessening the distance, right?
Yes.
So the distance between you and the fire is getting lesser, right? So if you take a microscopic step towards the fire, you're decreasing that distance by a microscopic amount, right? So it's not the fact that you, I think he's trying to get at is that it's not the fact that you have, what's causing it to get warmer is your previous time step.
Yes.
It's
Yeah.
not
Yeah.
your
That's a
current.
great
It's
way
not
of
your
thinking about
current.
it. Yeah.
I see.
Yeah, that's a great way of thinking about it. Yeah. So a fire, as it turns out, I'm pretty sure is I actually looked up the equation with Ina like a few weeks ago because we got kind of curious how the relationship between distance to a fire
Yeah.
works, but it's actually related cubically. So
Really?
yeah, it says an inverse cube of the distance from the fire, and then
Oh.
there's some other terms thrown in, but the inverse cube thing is the one that matters. So so it does grow quickly. It does grow non-linearly, but
Yeah.
it doesn't grow exponentially. It
I
grows
see.
cubically, meaning
Yeah.
if I'm 3 units of distance to the fire.
What if you change that? What if you don't measure the heat of the fire, but you measure the growth of the fire? Because I would argue a growth of a fire within the right situation.
Yeah, perfect.
Is-
Yeah. So you could. That's a great switch. So you could think about a fire with some stuff around it,
Yes.
and the more stuff the fire has around it, the more it's able to grow because there's more stuff for it to latch onto to grow more. And so that's a great way of thinking about it. Is the bigger a fire has grown, the more it's able to grow because its size causes it to be able to reach more things, and then
Yes.
that causes it to grow more, and then that causes it to grow even more, and
Yes.
it just kind of
Yeah.
explodes like that. Yeah. So that would turn it into something that's exponential,
Yeah.
and that's the pattern of being
Yeah.
exponential. So that's great. So just how we think of the pattern of a logarithm as being fundamentally something that kind of squishes things,
Mhm.
massive things, into being like very reasonable
Yeah.
things. The fundamental pattern that you should think about a exponential is
It makes it completely unruly.
not that it makes it completely unruly. That's not the fundamental property. The fundamental property of
Is
an
the growth?
exponential is the fact that the size of it is
I see.
the thing that's causing it to grow.
Yeah, I see. Okay. So
And-
the sheer fact that as there's more stuff added to the fire, just the size alone of it. So this is we're dictating this is the growth, but
Mhm.
this is it getting more and more stuff.
Yeah.
So as more and more stuff is close to it,
Mm-hmm.
the fire is exponentially going to grow. We'll just label this as.
Are we talking about? So what is x now?
So x we can dictate as wood. So like wood or stuff that is related to.
No, I wouldn't call it.
You wouldn't call it that?
Yeah, I wouldn't call X wood.
Would you dictate it still as fire? Because I would argue.
I would say that x would be the size of the fire.
Okay. So then function is not growth.
Oh yeah, actually, let's see. The size of the fire. Yeah, actually, wait. Let me think about that. So I would say. Yeah, wait. What would be on the
X
fire
should be no. I was gonna say X should be time, but
That's not related.
it wouldn't make.
Yeah,
The,
yeah,
the
yeah.
relation is the fact that there is more and more things that the fire is touching.
Mm-hmm.
And as the fire touches more and more things, it gets exponentially bigger and bigger and bigger.
Yeah. So I would say maybe the x would be size, and then the f of x would be the energy of the fire, or
Okay. I think that's more of a reasonable.
something like that. Yeah. I don't know if that's perfect, but
No, I don't think it's perfect, but I think it's
it's something like that, right?
Yeah. This is just.
This is just a way to think about. Yeah.
So we'll dictate that as energy.
Mm-hmm.
Okay.
Cool. So so
So this
going
graph-
back to the original train of thought.
it's all
Down
about
here, this is
relationships.
fundamentally about relationships. This is about relating something to something else.
Right.
And up here, this is about space. This is about now instead of right down here. Remember we said last time it was one-dimensional,
Yep.
right? Our variable is size, and that size can only go one way, right?
Right.
It can only get bigger or smaller. Now the fundamental units is in 2D, right? Each data point has another plane that it can move, right?
Right.
Instead of just getting bigger and smaller like this, it can get bigger and smaller in one direction and bigger and smaller
in another.
in another direction. So that's a very, very important distinction is because you'll see graphs all the time, and you'll see some graphs of functions. In practice, maybe you'll see fewer graphs of this, but
they're very, very different things, and you should keep
Understand
that.
that.
Yeah. So let's go back to this. So let's erase this whole thing. Let's only think about this, and let's actually make this. Let's make this a lot bigger now. And let's, again, we're going to call this x1, and we're going to call this x2, like that. So this is actually going to relate a little bit to what we talked about with the attention stuff. So I guess let's rank these words. Let's talk about how close together, how similar each of these words are. So what would you say the most similar words are?
The and the.
Yeah, done the.
The and the, yeah. So we have two thes.
Exact same.
Yeah.
Or,
Yeah. So we have two thes. What are the next most similar words?
Sorry, side note or side question. The fact that the first the has an uppercase T, would that make it?
No. It's all lowercase under the hood.
Two.
There's pre-processing steps that gets rid of all that.
two and poo.
Actually, it depends on the model. Sometimes it'll get rid of the case. Sometimes it won't. Depending on whether you think it adds information to have cases. It's kind of a, So anyway, what were you saying?
I was saying two and poo, just because of the size. But if we're going to actually be doing it based off of relation,
Mm-hmm.
cat and dog,
Yeah.
because they're both animals.
Yeah. So let's say cat and dog.
So it's like it's figuring out
Animals.
what exactly, like, the matrix or whatever
Yeah.
our space wants to dictate.
Yeah.
Because, for example, if we're just dictating it based off of size of word and not relation,
Mm-hmm.
then we can do poo and two or something like that.
Yeah.
But if we're doing it based off of actual relationship for what it is,
Mm-hmm.
it would want to live kind of like this, right? So cat, dog, they're both animals, therefore they're going to be pretty closely related.
Yeah. So let's remember that now we have we can draw data points on this plane.
Yeah.
So let's draw them.
So let's just do the and the.
And we're going to get a little bit more concrete here, and we're going to actually get these numbers. So we're going to say that this is 1, this is 1, this is 0.5, negative 0.5, negative 1, negative 1, negative 0.5, and 0.5. So let's just get like pretty concrete with where we put our points.
So we'll just dictate the first. So we already dictated it as a black.
Mm-hmm.
So I'm going to keep that color
Yeah.
for this.
Sounds good.
And then, so we'll just say the.
Mm-hmm.
It can be just in a single space here.
Yeah. Maybe we'll draw 2 like right next to each other.
Yeah.
There's actually a reason in practice that they would actually be in slightly different locations.
Really?
Yeah, which actually you might be able to explain because the reason has to do with what with attention.
Yeah, so the first it occurs at the beginning of the sentence. So that in of itself gives you some information.
Mm-hmm.
And whereas the last the, since it occurs towards the end of the sentence,
Right.
that gives you some other information. Although they're the same word, it gives you a little bit of like different information based on the positioning.
Mm-hmm.
Yeah. So in practice, like even if we're not just doing that for visualization
Right.
purposes. In practice, they would actually be be
Yeah.
very close to each other, but they'd in practice actually be a little
Yeah.
bit
So they're not the
separate.
same thing.
Mhm.
In this context.
because they also refer to different things,
Right.
right? This the refers to dog, and this the
refers to cat.
Yeah,
Gotcha.
so let's draw dog and cat. Okay. And actually, let's call this, let's also get more specific. Let's call this wait, I want the black one.
All right.
Let's call this, let's call this the number 1.
Yeah.
And then let's call this the number 2. And then we're going to make one of these the number 1 and the other one the number 2. Okay, cool.
Yeah.
So now let's draw dog and cat.
So within the
And
space-
there's I'm about to try to get you with a tricky thing here. So pay a lot of attention to what we're doing with dog and cat here and where we put them.
So I'm gonna dictate dog. Can I have red?
Yes, of course.
I'm gonna dictate dog as red.
Call one of them X and one of them Y, or like an X and a dot is how we can put it down.
And then I'm gonna do dot right here for cat.
Yeah.
And I'll just make that larger so it'll show up on camera.
Yeah.
So hopefully, I think that should show. Hopefully.
Mhm.
So for cat, we know that the is related to cat within space.
Yeah.
So ideally, even though they're both animals,
Mm-hmm.
we can kind of relate this to be closer to probably this the
Mm-hmm.
because it's relating to each other.
Yeah.
And then we can dictate the dog, even though they're both animals, they're still going to be in this general area, but we could probably dictate it closer to that the
Mhm.
because of the relationship that is
Yeah.
being formed there.
Yeah.
And
Great.
then the two animals are farther apart
Yeah.
because they're still animals, so they're still in the general vicinity,
Mm-hmm.
but they're not related to each other in this context of the sentence.
Great. Yeah, that's awesome. I think that's a great way to think about it. And not only is it a great way to think about it, but it gives you some intuition as to how you would turn a sentence into points in space.
Yeah.
You can put them in points in space through their relationship with each other, right? So like the numbers, and this is leading into a pretty important concept in machine learning, which is that
If you actually look at the axes don't actually represent anything concrete, right? Like they don't represent something like the x coordinate or a y coordinate, right? They don't represent how blue it is or how green it is. The axes themselves, the numbers in the axes themselves, don't actually, like you couldn't say like, what does x1 represent? What does x2 represent?
Right.
Like they give you a structure in which you can put points, and then the relationship between the points through their distances to each other is what matters. This is just giving them a space to live in.
I see.
So with that in mind, I think we're ready to turn this into a table, into a matrix. So let's now turn this into a matrix, and we're also going to pretend like the words hooped and next and to don't exist.
Okay.
We're just going to ignore those for the purposes of explanation.
Yeah. So I'm going to.
So draw a data table down there.
Yep. Actually. Let me do the data table first, and then I'll do the matrix.
mm-hmm.
So we'll do x1,
Mm-hmm.
and then we'll do x2 here,
Yep.
and then we'll dictate up here. We'll do the dog, and then I guess it wants to be separate. So I'm actually gonna do the.
So there's already something that you're doing fundamentally different than we've done before.
Really.
Mm-hmm.
Explain.
Something to do with the table.
So we're dictating rows, and then we want to.
What do the rows represent over there?
The rows are representing the vertices.
And what are the rows representing? Not there, but with our.
We don't actually have a picture of that we erased over here.
Just do it right here.
Let's just do 2 images, and they're both grayscale.
So, one was
Just
one,
this one
2,
and that one.
and then B1, B2, something like that.
Nope.
Two 2D grayscale images.
Oh, we want 2 of them.
Mm-hmm.
So we could still have same rows and cols. So we'll just call this R1, R2.
Mm-hmm.
We'll keep that the same. I guess it would then want to be image 1 and image 2. But I feel like that's fundamentally flawed.
Mm-hmm. Yeah, just think about how we organize. How have we been organizing stuff? Like, what do the rows represent in general, and what do the columns represent in general?
The rows represent the actual information, the relation.
What do you mean the information?
So, for example, for here we're doing verts.
Mm-hmm.
So we're dictating this is the information that we want within here for the
What
actual.
do you mean by information? Use a different word than information.
What would be a good word to use? Fuck. Give me a second.
Mm-hmm.
It would be the actual. I don't know. It would. Son of a bitch. This is where tired brain's coming in.
Yeah. So what's the general category of the rows over there? Like,
Yeah. So
ignore, like, let's move out from like vertices,
Vertices,
but
yeah,
like
yeah.
what, like how do we, like, what's the?
So we have one could be the relationship, and one could be. I'm trying to think back to like potential.
That'll be a screen protector.
Nope.
Nope.
Let's see.
Yeah.
Oh, hello.